Calculus video 20, continuity and differentiability. So a short video here about the relationship between continuity and differentiability. First, a definition. When we say differentiability, we're saying that a function is differentiable there. Right? A function f is differentiable at a, at the x value a, if the derivative exists at a, if f prime of a exists and equals a real number. We add that and equals a real number part. We're not talking about equaling imaginary numbers or infinities. And the infinity part's what I will focus on. If the derivative is infinity, that's not a real number. That means the derivative does not exist at that point. Okay, so differentiability is when the derivative does exist. Recall that the derivative f prime of x is originally defined as a limit. It is the limit as h goes to 0 of f of x plus h minus f of x over h. Right? It's a limit. And in order for the limit to exist, the limit from the left must exist, the limit from the right must exist, and those two things must be equal. Picture that in this case where the function we're talking about is the slope of the secant line, right? Where the derivative is the slope of the tangent line. So what we're saying there is, in order for the derivative to exist, in order for the function to be differentiable at a, the slope from the left must equal the slope from the right. Okay, take a look at this example here. We have the absolute value of, say, x minus 2 plus 1. You know, some kind of f of x equals the absolute value of x minus 2 plus 1. It's kind of what this function looks like. But focus on the slopes. The slope coming from the left, right, and all these points on the left-hand side, the slope kind of looks like this. And if you were to kind of guess what that slope is, I don't know, maybe that looks like a slope of negative 2. I was guessing. And on the right-hand side, we see that the slope is positive. Right? The slope looks like this at each of these points. And in that case, maybe we think the slope is positive 2. All right, let's see, what do we think about the derivative at a? What is the slope at a? Well, the slope coming from the left is negative 2. The slope coming from the right is positive 2. Because those two things are not the same thing when they meet at a, the derivative does not exist at a in this function. Right? Because the limit from the left does not equal the limit from the right. We would say f prime of a does not exist. Anytime you have this sharp corner, this sort of corner right here, the derivative will not exist at that point. Now, the derivative will exist at other values of a, right? The slope might be 2 or negative 2, but at a, the derivative does not exist at those corners. Okay. Similar here. On the right-hand side, we have some function. We're not really sure what this is, but we see we have this corner right here, the sharp turn. At that value a, f prime of a does not exist. Okay, derivative does not exist at a sharp turn, at a corner, because the left-hand slope and the right-hand slope are not the same thing. Another way that the derivative would not exist is, for example, this function f of x equals the cubed root of x. I've drawn that here. Specifically, take a look at what happens when x is 0. And I probably didn't even draw it well enough here, but what happens is that curve actually at 0 becomes completely vertical for just an instant and then goes off to the right. Right? What's happening is the curve, goes kind of this way, and then right at 0, that is a vertical curve, and then it tapers off to the right like this. Because the curve is vertical, the tangent line is actually vertical as well at 0. That means at 0, the slope is vertical. That's an infinite slope. You go up infinity, you don't go over left or right at all. When the slope becomes infinity, we say that the derivative does not exist there. And the reason it doesn't exist goes back to what we talked about a minute ago. For a function to be differentiable, at a, this occurs when f prime of a exists and equals a real number. Because infinity is not a real number, it's a concept. The derivative, if it ever gets that perfectly vertical slope, does not exist at that point. Therefore, f prime of x on the cubed root of x, f prime of 0 does not exist. Okay, one more. On piecewise defined functions at, say, this value a where the graph jumps, you'll notice that the slope from the left, the slope as you approach from the right, not the same thing. That's a problem. The derivative does not exist at a as well. Now in the piecewise defined function, you'll notice that the function's not continuous at a either. There's a jump. So f is not continuous at a either. F is not continuous at a. However, on the other three graphs that I drew, the function is continuous at the a value. Go back to the cubed root of x, and we will see that the original function, f of x, is continuous at 0. Right? I drew the whole thing without picking up my pencil. There's no holes, no jumps, no asymptotes. The function here is continuous at 0. So even though it's continuous at 0, the derivative, though, does not exist at 0. Same thing back over here. At the cusp, this corner here, corner sometimes called a cusp. At the cusp, or the corner, the function is continuous, but the derivative does not exist today. On the absolute value graph, the first one we drew, the derivative does not exist today because of the corner or cusp, but the function is continuous. F is continuous at a. And again, f is continuous at a. So here's what it appears. There can be a function that's continuous at a, but not differentiable at a. That leads us to this statement here. Continuity, a function being continuous at a, continuity at a point does not imply differentiability. Right? 3 of those graphs were continuous at a, but not differentiable at a. Continuity, just because it's continuous, does not mean it's going to be differentiable. Think of the absolute value graph, right? Nice and continuous, but not differentiable at that one point A where you have the corner. However, what we are going to find is the contrapositive of this, which says that if a function is differentiable at a, then it is continuous at a. So if a function is differentiable at a, that does imply continuity. I guess I'll use the same verbiage. Differentiability does imply continuity. Meaning if you can show that a function is differentiable, then you can show that a function is continuous at that point. And that ends up being important for us later on. If you remember the definition of continuity, right, we had to have 3 things occur for a function to be continuous at a. You had to show that f of a exists. You had to show that the limit as x approaches a of the function exists. And you have to show, thirdly, that the limit as x approaches a of the function is equal to f of a. In order to show that something is continuous at a point, you have to do all 3 of these things. And sometimes that can be difficult. But instead, what we can do, in order to show continuity, which we need at times, instead of showing that a function is continuous based on showing these 3 things, if we can show that a function is differentiable, that we can take the derivative there and the derivative exists, if we can show this, then we get continuity for free. If we can show differentiable, we know that if it is differentiable, the function is also continuous there, and sometimes that is much easier to show that a function is differentiable, that the value of f prime of a exists, than it is to show that the function exists, the limit exists, and the limit is equal to the function of a. All right, that is all for differentiability and continuity.